Hi, welcome to the continuation module on ERP analysis. In last module, we have seen the introduction of ERP analysis and what are the application where you can use the ERP experimentation. We have also seen three different blocks: how to generate the stimuli, how to acquire the data, and how to extract the data. We have shown you one actual experimentation which is being happening, a glimpse of that. So the same experimentation, we have recorded some data. So in this particular short module, we are going to see how we can use MATLAB to record that particular data and make sense out of it. So if you can see my MATLAB screen, this is particular data which has been stored using the acquisition. NEDF file, as I mentioned, using that Electrics Inobio 8 cap saves the data in NEDF file. And also I ask you to download the EEG lab. Now if you download the EEG lab, it comes like this. This is your particular EEG lab, in which you can see the different functions. So all these functions in different classification, miscellaneous functions are there, GUI functions are there, pop functions are there, statistical functions are there. You can go and explore it at your own. Also these are the plugins I mentioned, different plugins are there. Now if you want to operate or process the ERP data, you should have this ERP lab. So I have currently this latest version of ERP lab 8.30 here. You can check that. So basically everything should be added here, and it should that everything should be added into the path as well. So which I have already added here in path. So we'll just start the EEG lab and try to extract the data, extract the response. You can write here in command window EEG lab to open it. This is the home screen of EEG lab. Once you open your file, if you want to import the data, you can go to the file menu, and there are based on the plugins you have installed, you will get different formats which you can acquire. If you have recorded using Neuroscan, there is a CNT file you can import. Currently we have used Inobio, which is from Neuroscan file. So we can either give NEDF file or easy file, anything is fine. So let's acquire the data using NEDF file. You have to browse the particular data. For that, make sure that your MATLAB is at that particular level where your data lies. You can load the channel location. During the entire experiment, subject was lying without doing any kind of significant movement and all. We are not considering accelerometer channels, but we are loading the channel location, and you just press OK. It will acquire your entire data. Takes some time, because that particular experiment was repeated for 800 standard, 100 distractor and 100 target. Okay, what is standard, distractor and target? I told you, standard small blue ball, target big blue ball, and distractor is checkerboard, which distract you to identifying target or big ball. And subject was asked to click whenever that particular big ball come. Now just to give a name, let's say subject 1, I am writing here S1. Keep this name as short as possible, because you are going to do so many operations. So you can append if you are doing filtering underscore filt, if you are doing Binbased Epoch underscore Binbased Epoch, if you are doing artifact rejection underscore artifact rejection. Ultimately it will go to a particular it will be a very long name. Instead just keep a small name here. We'll keep at subject 1, hit OK. So there's no current data set has been converted into S1. Now there is a lot of information here. How many, what is, first of all, most important thing is what is the sampling rate? It is 500. Okay. How many events? So it has detected 1102 event. Now I told you that 800 standards or small ball, 100 target or big ball, and 100 distractors or checkerboards are there. So sum is 1000. Why this additional 102 events? So I told you, I asked subject to click. So that also we have considered as event. So in response to 100 targets, subject has clicked maybe 102 times. It 2 times falsely clicked there. So this are the total number of events, and how many frames per epoch and all will come to that as we'll keep on going to process. Okay. Total epoch starts, like currently your don't consider epoch, consider experimentation starts at 0 ends at 899.996 second. So it is around 15-minute experiment, and that's why it took little bit time to import the data. So once you import all this thing, you can check the data how it looks like or something. It's a raw data, so you won't be able to make much sense out of it. You need to do filtering, but how to see the data? You can go to plot and channel data scroll. I'll do it again. Plot, channel data scroll. Once you do that, you can see the screen in which 8 electrodes are there. Now if you have understood the 1020 system which is talked by Dr. Pandya properly, you should know what is FPZ, FZ, CZ, PZ, OZ, T7, T8 and P7. Now if you can look at myself, I can explain that your FPZ is this particular point on your forehead. It's on midline. Okay, followed by FZ, which is there little bit above your forehead in the midline, then CZ, PZ and OZ. Basically this thing covers your entire midline from your forehead to the backside of that. Now this P300 is visual potential, so it is more prominent in centroparietal or parieto-occipital lobe. So these three are the electrode of our interest. We will see that. Now if you see that, but you cannot see any kind of EEG and all, right? So where are the responses? But here you can see the events 1, 2, here 4. 4 is your response with respect to 2 is your target. So you can have an idea. If I just maximize it and increase the time range to display, okay, you can get this, all this thing. See, 1 appears most number of times, the frequent stimuli, which is your small ball. 2 is your target. So in response to that, you can see the cyan color 4 response is also there, and 3 is your checkerboard. In response to that, a subject should not click. So all these are just an event, but where is the data? We can see the event, but where is the data? If you can remove the DC offset, you might be able to see the data. See, all these brain waves are dancing all around the screen, but the thing is, it is not filtered, so it has so much non-neural burst as well. So once we see the filtered data, we can make more sense out of it. But you can see here from 1/50th second to 1/70th second, this is the brainwave. Also you can increase or decrease the sensitivity by changing this parameter. See, now it's all over. If you want to still see the clean data, you can increase the scale of 200. You can see the again clean data. Also you can see, might be this can be subject's blink, because it is coming higher in the above electrode and here it is getting inverted. You can make more sense out of it once we do filtering, but this is basically how the data has been imported. The main confirmation is your data is there, which we have recorded, and your triggers are also there. So this is important, which you can see here. Also when you hover over this, you can see the time and value if you want to measure a particular value of electrode. Okay, cool. So we got this data as well as trigger. We will now quickly see how it looks like in frequency response. For that, you can go to filters and frequency tool and plot amplitude spectrum of EEG data. Now this data will give you an overall idea that whether you have a power line interference or not, and how many electrodes. Currently let's consider all 8 electrodes. Combinedly it will show you one frequency response. Now one more thing, if you have noticed here, it comes in x-axis, it's a frequency in log scale, here amplitude. If you can see this here, a lot of DC offset is there, so which we can remove once we do filtering from 3 to 30 or 1 to 30. And there is a small tip here, okay, so that is around 150, which is nothing but a multiple of your power line interference, which is 50 Hertz. One more thing if you have noticed is when I given the command, I have given the maximum frequency here 250. Very important thing, why I have given this 250 is because if you can see here, the sampling rate is 500. So as per Nyquist theorem, if your sampling rate is Fs, the maximum frequency which you can successfully obtain is 250. So if I go here above 250, it throws error. Okay, so it's a very basic thing for signal processing, but you should know that whatever your sampling frequency, accordingly you should plot the spectrum. So currently it's fine, spectrum looks good, but still a small this thing is there, but not that much hazardous. In some of the cases around 50 hertz you will see a big spike. In that time you have to do notch filter. Here it's not required, so we can directly go ahead with band pass filter. How to do notch filter, how to do band pass filter, we'll see that in tools, filter, basic FIR filter. For the illustration purpose I am just selecting a basic FIR filter. If you want to remove 50 hertz noise, you can check this option, notch filter, and you can give here 49 and 51. What it does is from 49 to 51 it notches the data, or it removes that particular frequencies, which is basically a 50 hertz frequency. In that case this pass band will become a stop band. If I talk in actual sense, it will become a stop band. It will stop the frequency from 49 to 51. Whereas here I will just give we could not see any kind of power line interference in this data. So what we can do is we can directly take 3 to 30, which is lies in the range of brainwaves. So this is particular data we are going to filter. We want to see the frequency response. So we will quickly see the frequency response. You can see first this, okay, it shows your magnitude is 0. Now we want to pass this frequency. Why it is 0? This is in dB, okay, decibel. So log 1 is 0. That's why, but it allows all this frequency. Now it allows till which point. If you want to see, you can put a indicator here and try to check. See, till 30 it is showing some value. If you go above, see, till 29 it's 0.007, so it's almost, it's allowing 29 to 31. Also from which point it has started allowing, from 2.96 or something. Beyond 2 it is not allowing. It's a negative decibel value, so magnitude will differ in the tens of basically a drastically change. It will allow this frequency which is there in this pass band, and it will not allow all the other frequencies, okay. This all the ripples you can think to remove. If you want, you can select a different form of filter and all, but for us for this particular application, this thing looks fine. Also you can see how the phase changes. If you want, you can use a minimum phase filter as well. So now my data set will change. Earlier it was a raw data set, now it's a filtered data set. So I'll just write here filt, okay, and then I hit OK. Now observe this one hashtag 1S1. This is just a first data set. As soon as I give OK there, it will be updated. So now you have second data set which is already filtered. You can observe all the data sets here, which we'll see at the last as well. But this is what your filtered data set now, okay. How to check that whether the data set has changed or not? Again you go to and check the amplitude spectrum. For all 8 channels you check the amplitude spectrum, and you can see now some mountain kind of shape is there. Whatever the DC offset of 70 magnitude or something has been removed, and which should be removed because you want to have an idea about what exactly is happening underlying the brain, and which is like underlying the skull, which is 3 to 30 hertz or something. So you are getting this kind of amplitude spectrum of your data. Next step is to give an information to your system about events, when particular event happened, how many standards, how many target, how many destructor. To identify that, there is something called event list. You have to create the event list, tell your computer that at this particular time this standard come, at this particular time this destructor come. How do you do that? Like if you have seen the channel data scroll, now it will look much better. First of all, because we have filtered the data, it will look much better than previously. See, it looks like a clean EEG data, and also triggers are there, but it looks much better than what you have seen before. It is not interfering to each other. Also you see the scale has been reduced drastically. Earlier it was some 500 or something, now it's 200 or something, and now it's just 80. If I further go down, see, you can see the clean EEG looking really good, right? So this is the filtered data, and this is the advantage of filtering the data. So let's say this is the filtered data. Next step is to give the computer a sense about the triggers or timing information. You can do it by creating event list. How will you do that? Go to create event list, and you have to go to advanced option, and you need to change this, okay. This was some previous experiment, so I will just remove this. You need to add your own understanding, or you need to tell. So event code 1 stands for standard. Again event it will form a bean number 1, I will name it std, okay, or we can write standard also, standard, okay. As soon as you give all this thing, you have to update that particular line. Again go to 2 was target, we have seen in response to that subject was pressing the thing and all. Again 2 is target, cool, update the line. Same you thing you do for distractor as well. Once you do that, event list will be automatically created, which we can further see. Now if you forgot to update the line, this pop-up will come that you update it, you have written it here but you have not updated, you can go back and again update it. So all this thing have been up. This is, I need to again update the second line because it was updated in the previous line, okay. I will update it here again. 2 was target, again 2 was target, and again I have to update the line. So you can see all these 3 events are there. Currently I am not interested in response or pressing the button. So I will just apply this to event list, it will say, and then it will ask to code the labels whatever has given. So these labels have been generated through the system, 1 2 3 4 what you have seen in the, when we were scrolling through the data. So it will again, it will ask to change the name, so just append the elist to that, so it will create one more data set. So this 2 has been shifted to 3. First we take the data, filtered it and generated elist. How the elist is generated, what is there in elist? You can go to here command window, and here you can see a new event list was created at this particular place. Go there, open that particular file, click on that, it will show you the generated event list. Yeah, so you can see that when it is generated, using which version of ERP lab program it is generated. Also you can see there are 800 standards, 100 targets, 100 distractors. Now when it is generated, what particular time, what is the difference between 2 particular events, all this thing you can check here. Now generally 800 was given, now it is slightly more, 18, so difference is 18 millisecond, 18 millisecond is jitter, okay. Here it is 288 because it is, we have not given the name but it is 4th number, event code is 4, which is a click of the mouse, that is why it is less, otherwise generally it is around 816, 880, 816. Some delay will come in order to give the trigger, but that can be compensated later. So this is elist has already been generated, and you can see that total 1102 events are there, out of which our interest is only for this 1000 event. 102 key press we are not considering much, but here if you can see this is a elist. Next step is to generate the bin-based epoch based on this elist. So I will generate the bin-based epoch. Here the important thing is when a particular event happens, how much amount of time before that you want to consider, because there is something called baseline. I will show it to you in graph itself. So if you can see here channel data scroll, the another change which has happened is you can see now the name of the particular event has started coming, okay, standard, target, the 4th number we have not given is the response. So for me to record or make the sense out of it, it is important that I will consider not only after onset, that is called post stimulus data, but pre stimulus as well, that before you have given this particular sound what was the trend. So what I will do is exactly before this I will take some amount of data and then after, so that will give me an idea that how much change this particular event has posed when this particular event happened. So pre stimulus some time and post stimulus at the time of your interest we need to consider. Now this ITI is 800 milliseconds, so post stimulus we should take anything which is less than 800 millisecond, it is like a common sense, and pre stimulus we need to take some data. Generally thumb rule is if you are taking 500 millisecond this side, post stimulus take 10% of that pre stimulus, so minus 50 to 500 or minus 100 also, depends on how your baseline, and this all are like as I mentioned, your frequency for filters you can take 0.5 to 30, 1 to 30, or 3 to 30. Similarly, your baseline you can take minus 50 to 500, minus 100 to 500, or even minus 50 to 700, minus 100 to 700. So it's like a problem of choices. You have to identify. You can only identify what is the optimal values of your parameters by doing it. Okay, so the idea of showing all this thing is to make you people understand that what is baseline, what is called pre-stimulus interval, what is called post-stimulus thing, and why baseline is important. So now and all this thing matters when you are generating bin-based epoch. So now you will generate a bin-based epoch. As I mentioned, let's take minus 100 to 500 millisecond. It's written already in millisecond. Baseline correction, we are giving pre-stimulus baseline correction. Just run the command, it will generate the bin-based epoch. So now if you see here, you can see here the thing has come is epochs 1000, because we have generated bin-based epochs, and this 1000 means 800, 100, 100. Also frames per epoch. Now we have gone for minus 100 to 500, 600 millisecond, whereas sampling rate is 500 hertz. So each epoch will take 600 milliseconds. 600 millisecond is nothing but 300 samples. That's why frames per epoch comes at 300, total epochs are 1000, sampling rate is 500, epoch starts at minus 100, minus 100 millisecond or minus 0.1 second. Epochs end at 0.498 second, which is around 498 millisecond. Reference we are not given, that's fine because we already fed reference externally. Now this is your bin-based epoch is done. Next step is to artifact rejection. So you can use a simple voltage threshold here, as you can see, and here again you need to change the interval minus 100 to 498 in all channels you want to see, and this value again. I talk about parameters, about filters, cutoff frequency, etc. I talk about parameters, pre-stimulus interval, add one more into that, voltage threshold or voltage limit. You can give minus 100 to plus 100, in some of the other cases you can give minus 50 to plus 50, up to you. You can select all the available channels from here, already selected, so you can see here. And after your artifact rejection, if you want to see the viewer that out of all the data, what are the data has been removed, okay, you can see that. Before that, after every step it is important to see the channel data scroll, what change it has enforced. So before that you have seen only target and all is written, now bin is created. Also this dashed line has come, which we wanted. I told you we are interested in 100 millisecond prior to stimulus, which is happening. Okay, I told you we are interested in 500 millisecond after the stimulus, which might be somewhere here. Okay, same thing you can see here, minus 100 and somewhere around 500 here, again minus 100, 500. So time axis, which was continuous and going like 10, 15, 100, 200, has been limited now to minus 100 to 500, because that is the only thing which matters. Okay, so let's see, epochs are created. We can quickly see the artifact, do the artifact rejection. Go here, minus 100 to 498, minus 100 to 100 is fine, that's a standard range of artifact rejection. Select all this thing and just hit the accept button. So again, as I mentioned, it will keep on adding all these different naming conventions. It will get suffixed to, because why this all is important, because if I just read the name I can get an idea. Okay, the subject row data was taken, filtering was done, e-list was created, bin-based epoch generated, and artifact rejection is done. So it's an important nomenclature and makes things much easier. So if you see here, this should summarize your overall artifact rejection. Out of 800 standards, 700 were accepted. Out of 100 targets, 90 were accepted. Out of 100 distracted, 93 were accepted. All over 1000 events, 883 were accepted, which is good enough to average it out and make the sense. So now we are getting we have got this artifact rejection stuff. You can also see, go here and summarize artifact rejection in table, graphic. You can put it in one value also. You can see all this thing. Like I have just asked to summarize the artifact rejection in graphic. So whatever we have seen in command window, you can see in a very nice way that 883 were accepted, this were rejected. Out of all electrodes, which channels was having artifact and what is the flag of that. So all this thing you can analyze and check. Thing is, now we have got the data filtered, ELIS generated, Binbased Epoch generated and artifact were rejected. So we are good to go with the average. So this step is important. What it does is it converts your EEG into ERPs. Here all these options you can select, that you have to include all the epochs, you have to exclude the epochs which has been rejected during artifact detection. You can do both. Also what you can do is you can select this data quality parameters. If you want, you can also generate power spectrum and evoke power spectrum. For now I will just consider with the default option, and I will just trying to generate the ERP. Also you can see the dataset number is 5. There are multiple data sets 1, 2, 3, 4, but what we want to include is dataset 5, which has been gone through all the set of operations, which is our like most neural or best fit to neural data set. So I will just run this. You have to name the ERP. I will just name S1 underscore extracted. Okay. So this is, and you can save the ERP as well. So now you see earlier data sets were there. Now ERP set, you can see one ERP which is generated. So once ERP is generated, next step is to analyze it and check what are the data lies there and all. So you can plot the ERPs using ERP lab plot ERP function. Yeah, here you can see a lot of options and it's very easy. First is there are 3 bins which we have created. It will ask what are the bins you want to plot. You want to either only plot standard, you want to only plot distracted, you can do that. You want a legend or not. So that is what this guy tells. Okay, this particular dialog box. This scales. The scales you want from -100 to 498. In time domain, what are the range you want. Further you can say you want a specific scale or not. Also SEMs, very important. It shows the trend. You are going, you are doing almost 100 to 200 or even for standard 800 epochs. During each epochs it gives different response. So what is the variability amongst the epochs? So the trend and variabilities will be given using this option. Okay. So what you can do is here you can enable it or will enable it later. I will show it to you. Some of the neurophysiologists or clinicians are prefer to see the negative up when they are specifically checking for negative potential. So they just have to see a positive or like upside pick and make a sense out of it. In that time you can go here, do negative up, positive up, anything is fine. Also you want to see all channels or a particular channel. Now I mentioned that this is a visual P300 experiment where all the data and all the dominancy can be seen in the centro-parieto-occipital lobe, which is my 3, 4 and 5 channel. So we will come to that, but first let us see all the channels. Also you can go here and go for a topographic view. So it will give you a better indication of how the data looks like. So let us just quickly plot it first, and it will ask for channel location. If you have deep fit inside, you can just give the channel location and you can see the data. So FPZ, FZ, CZ, PZ, OZ, T7, T8 is on your temporal lobe and P7 here. Here is the scale which you can use, but this is the entire midline on your head. Okay, why did I do that? I just want to show you the response accordingly. If you want to see any particular thing, you can click on that, you will see only that particular electrode. Okay, you can stretch this, it will give you a better result. Now this experiment is around known as P300. Okay, P300 means some positive peak around 300 millisecond. So with respect to your target and restrictor. So you can see here, this is black color line is your standard as it is shown here. Further, red color line is your target. target means a big ball. So when you click on the big ball and it comes around, if you see here around 350 or somewhere, you can see the pick which is significantly higher than your standard. Same for distractor it is even higher. Okay, so you can put a indicator here and see when the actually the peak occurs. So for distractor it occurs around 400 millisecond, whereas I can consider this peak it's 390 or something. I am talking about this red color trace, not the blue one. Yeah, so if you can see here it's around 388. Also you can see there is a plateau. It results due to multiple peaks because all this standard and target, basically target known as P3B working memory, and this distractor known as a P3A component of P300 which is for attention. So this comes because of several neurophysiological processes underlying happening underlying your scalp. So that's why sometimes you get multiple peaks, sometimes you get plateau as a result of multiple process eliciting due to your event triggers. So this particular thing you can see here is nothing but your seize response from your CZ electrode, and you can see a very nice P300 here. Same thing as I mentioned that you will get better response in CZ, PZ, OZ. So here if I open the PZ electrode, you can also see the similar form of response, and it also picks around 300 to 400 millisecond. Here if you see this target trace elicits way much before in terms of time 378 millisecond, whereas this distractor peaks at 414 millisecond. So it is an objective measure. For some of the subjects it might be earlier, for some other subjects it might come slightly delayed, but name P300 suggests that there should be some positivity after 300 millisecond. It comes generally in 300 and 400 millisecond. This is a topographic view. Now as we have seen and analyzed, we are sure that the better results are there in CZ and PZ. Now CZ and PZ is nothing but your third and fourth electrode. So now we will specifically plot only this two electrode, and it will give you an idea what is SEM. For that I will just do it classic ERP. I will turn the SEM on. Instead of selecting all channels, I will just select third and fourth channel. Okay, so now if you see third and fourth channel, and I want to see here you can select how many rows and columns you want. I can just opt for, I just want it in 2 row and 1 column. So I will just take 1 column here. So I can put the things exactly next to each other, just below each other. And now if you see the Y scale has also reduced because FPZ was having more fluctuations in the previous graph. If you see this now, if you see this, you can see the graph. Now why did I do this is just to show you the SEMs. So this light color things is nothing but your SEMs. You can see that even SEMs are getting separated. The SEM is nothing but your variabilities. Okay, during all the 100 trials it would have gone slightly up, slightly down also, but it almost follow this thing. So this concludes that yeah, you can see this P300, it is there, and also it is getting generated using your target or distractor stimuli. Another thing is you can use this thing to resample it if you want. You can do all this reinformation. ICA is also a very important topic, independent component analysis. In your EEG there are how many approximately how many components are lying there. So accordingly you can remove your unwanted components and check the things. Now one last very important point. You have seen how I have used GUI to do this thing. Suppose I have a data from 500 patients or 500 subjects of this sort of data. What do? How can I get it done using scripting? Okay, so what you can do is whatever I have done so far in EEG lab, there is a command EEG.history. If you hit that command, it will tell you that I have done this much thing. Okay, fine. What I will do is I will again import the data, or let us say I will do the filtering, okay, basic filtering to your initial data, okay, because this thing already we have done. It is just to show you a glimpse of how you can convert GUI to scripting. Okay, anyways, if you scroll here, okay, you can see equivalent command everywhere. When you are plotting, this is equivalent command. If you even go before, we plot it twice. This was plotted using topographical view, so style is topographical, whereas this was plotted using your normal view, classic ERP, so style is classic ERP. Okay. Also in when we plotted second time, we have turned SEM on, so this SEM is on. Basically, for each command which you give in your GUI or EG there will be a equivalent command here. When I did averaging, it was this. We kept this dataset DQ flag on, dataset option, so it is 1. While saving it, we have given this name, so this is the name. Saved ERP will be saved here. You can see here. Also, if I go further below, ahead, this was what we have used: artifact rejection for all 8 channels, 100 minus plus or minus 100 millisecond. For how much time? Minus 100 to plus 498. Also, it will show you the time. At this particular time, you did that. Okay. So similarly, this is just a summarization of artifact rejection. Before that, we did pop epoch bin. So it is like a highlight. After cricket match or any match, you see the highlight. Same thing. After doing all this thing using GUI, if you go to the command window, you can see the highlight of equivalent commands what you have done. So when you have multiple files or multiple subject, you can use all this command, run a for loop, okay, and you can get the things done very easily. This is to check the artifact is there or not, the same thing. So this is from checking spectrum till getting the ERP done. Everything can be done using scripting. So this is an overall idea. This is advisable when you are doing batch file processing basically, and also further, if you want, you can go to plot and do ERP imaging and all sorts of things based on your requirement. You can explore this thing at your own. There is an excellent documentation available for EG lab as well as ERP lab, and it is very important when you are processing data and to make sense out of your recorded EEG data. So that is basically a short module on how you can extract the ERPs using data. If you have any question or anything, feel free to write in the forum. Maybe I'll see you guys in some other course next time. Till then, all of you take care. Bye.